A1 multiplied by Legendre symbol of B upon the second prime factor of M, that is P2, and raised to the same power as in the factorization, that is A2, up to B upon PR, rth prime factor of M, raised to the same power as in the factorization AR. Okay, so this is the definition of the Jacobi symbol, and in one way you can say that this is the generalization of the legendary symbol, because in legendary symbol we had A upon P, where P was a prime number compulsorily, whereas in Jacobi symbol M can be prime, composite, anything. Only requirement is that B and M should be relatively prime. There is no other requirement. M can be prime or composite or anything. Okay, so for example, if my M is 15 as we had taken here, and let's say B is 2, then 2 and 15 are relatively prime, and this is equal to 2 by 3, legendary symbol of 2 upon 3, and legendary symbol of 2 upon 5. Now either you can use this formula to calculate. So if you use this formula to calculate the legendary symbol, 2 upon 3 will be, okay, this will be 2 raised to 3 minus 1 by 2 mod 3, right? Or we can go by the calculation that we have already done, which is 2 upon 3 is minus 1. Minus 1. How did we do that? Why is 2 upon 3 equal to minus 1? Apart from this definition, it was because there is no such square term, there is no such x square, such that no such square term which is congruent to 2 mod 3. So because it is mod 3, we consider x equal to 0, 1, 2. We take 0 square mod 3 is 0, 1 square mod 3 is 1, 2 square mod 3 is also 1. So similarly, if we take in case of 2, 5, 2 mod 5, 0, 1, this also we had done in the previous lecture. 1, 2, there is no such term, there is no such number from 0 to 4, such that if you square that number and you take mod 5, then it is congruent to 2. There is no such number between 0 and 4 which satisfies that. So 2 upon 5 is also minus 1. 2 upon 5 is also minus 1. And therefore it is equal to plus 1. Okay. So while in Legendre symbol we had A upon P is plus 1 if A is a square mod P, and A upon P is minus 1 if A is not a square mod P. This is no more true in case of the Jacobi symbol. This is not true in case of Jacobi symbol. Okay, so B upon M equal to plus 1 does not imply that B is a square mod M. does not imply that. Okay, so now what is the purpose of Jacobi symbols then? So Jacobi symbols are normally used to find the factorization in factorization of large numbers and in primality testing. So out of these, after certain more theorems and properties, we'll see that exactly how Jacobi symbol can be used to test for the primality. Okay, any questions up to this point? Any questions? Okay, so then I'll proceed. Hmm. So these are some of the properties that we'll see now. Jacobi symbol of m upon n is equal to -1 raised to m minus 1 into n minus 1 upon 4 into n upon m. Okay, this is called reciprocity for Jacobi symbols. M upon n, if we want to calculate n upon m from m upon n, or vice versa. Like, okay, so you will multiply a Jacobi symbol by -1 raised to m minus 1 into n minus 1 by 4, then you will get its reciprocal. Okay, then there is supplementary law. -1 upon m is equal to -1 raised to m minus 1 upon 2 is equal to +1. Now this is okay. There is proof for this, but we don't require the proof. But this is the property. If m is congruent to 1 mod 4 and it is -1, if m is congruent to 3 mod 4. This is how you calculate -1 upon m. -1 upon m, either you directly do m minus 1 upon 2 -1 raised to that, which is a simpler way, right? Or in other words, it is also given by this formula. Okay. Then there is one more law, you can say 2 upon m is, now this is a bit complicated for it, so I'll directly give uh, okay, it is +1 if m is congruent to either 1 mod 8 or m is congruent to 7 mod 8, and it is -1 if m is congruent to 3 mod 8 or m is congruent to 5 mod 8. Okay, so this is the reciprocity and these are the supplementary laws. Supplementary laws. This is the supplementary law for -1 and this is the supplementary law for 2. Okay, now where do we need this? Why do we need these laws and everything? Because it makes some of the calculations easier. So let's say I want to calculate Jacobi symbol of 246 upon 257. How will you solve this? Any questions up to this point? Okay, so if any question you can just ask in between, no problem. So here what we'll need is, because if we want to do it directly, we have supplementary law for -1 and supplementary law for 2. So we'll separate a factor of 2 from this and write this as, sorry, it is not, it's 257. 2 upon 257 and 123 upon 257. Okay, so 2 upon 257 will be, which of these does it fall into? What is the remainder when divided by 8? Remainder is 1. Therefore, this bracket reduces to +1. Now we have 123 upon 257. Okay. So what will we do next? Okay, it is so by definition. So if you can see, like 257, in this case, let's say you know it's a prime. But if you may or may not know 257 is a prime, but 123 is a composite number. Okay, test for divisibility by 3. You can directly see. So you find its reciprocal. Now can we reciprocate it directly? What will be the formula for reciprocation? -1 raised to m-1 into n-1 by 4. Okay, so I want to find the reciprocal of this. Okay, so -1 raised to m-1 into n-1. 122 into 256 upon 4 into 257 upon 123. Is this step clear? Reciprocity law, m minus 1, 123 minus 1, and n minus 1, 257 minus 1. So if we divide it by 4, like still the result will be an even number in any way, right? It's the power of 2, so even after dividing by 4, 122 into 256 divided by 4 is an even number. Therefore, minus 1 raised to an even number will be plus 1. Okay, so therefore it will be 257 upon 123 as it is. Okay, then what else can we do? Now can we apply the factorization? So 123, we can see that 3 is a factor. Okay, 3 into what? 3 into 41, right? Is there any other way? 257 upon 123. We'll have to go by the basic definition. It is 257 upon 123 is equal to 257 upon 3 to 257 upon 41.
Excuse me, sir.
Yes,
Sir, I did not understand why we did this step, like 257 upon 3 and 257 divided by 14.
this is by definition. B upon m is B upon the prime factor of uh, m, first prime factor raised to the power of the
Okay,
prime factor, where this is the
okay,
factorization.
sir.
So
Got it. Got it.
yeah, yeah.
Got it.
But there is still some simplification possible. Two 57 upon 123. 123 is composite. Now we have primes, 257 and 3, 257 and 41. These are primes that we have. Okay. So can we apply the definition of Legendre's symbol here? Mm, okay. Yeah, there is one more property that we can use. So one way at this stage, one way would be consider this as a upon p and calculate as a raised to p minus 1 by 2 mod p. This is one way where in this case uh, 257 is a and p is 3, and here 257 is a and p is 41. Another simpler way is actually there is one more property. Just consider this as a property. Okay, you can use this property. Uh, 257 upon 123 is actually congruent to. Now note that 123 is not a composite number. I'm directly simplifying from this step. So, okay, this is alternative way that I'm using. It is congruent to, because 257, if you see this directly, 257 is congruent to, so 123 2s are 246, and it is congruent to 11 mod 123. 11 mod 123. So using this property, okay, this can be reduced to 11 upon 123. This can be reduced to 11 upon 123. Okay, consider this as another property in case of Jacobi symbols, is that b upon m is congruent to b mod m upon m. Okay, so we can use this property simply if you say this is not a Legendre symbol because 123 is not prime. Okay, so you have to, if you want to reduce at this stage, you can just take the mod, and it is 11 upon 123. This is a property that I can say. And now again we can use reciprocity. So if you check the reciprocity law, it will be -1 in this case. The result will be -1 raised to because this will be 10 m minus 1, n minus 1 will be 122, and divided by 4 will be uh, it becomes an odd power. So this will be -1 and 123 upon 11. Okay, another reason is 123 is congruent to 3 mod 4, therefore it is -1 as a factor. Now again use the same modulus property. 123 is congruent to 11 square is 121, so 123 is congruent to 2 mod 11, so it reduces to this. And then finally you can actually directly check, or you can calculate this by a, that is 2 raised to p minus 1 divided by 2, that is 5 mod p. 32 mod 11. 32 mod 11 is actually 10, but now we want it in terms of either -1 or +1. Okay, so I can say it is congruent to -1 mod 11. -1 mod 11. Therefore, it is equal to minus of -1, which is equal to +1. Okay, so ultimately your answer is +1. 246 upon 257. 246 upon 257. The Legendre's symbol is +1. Okay. So this is how it is calculated. Why did you take 2 raised to 5? Because it is uh, by definition, by this definition, by this definition, by the symbol of by the definition of the Legendre's symbol, because now the in a it is of the form a upon p. Yeah, it is p minus 1 upon 2. So p is 11 and 11 minus 1 is 10 upon 2 is 5. That's why. Okay, first step is not clear. uh, yeah, okay, so this is also like a, okay, so I might not have. Okay, so let's say in the definition itself we saw about the factorization of the, okay, I won't call it denominator as such, but like we saw about the factorization of m. If we factor m, then we can write this as b upon p1 into b raised to a1 and so on. Similarly, we can factor the numerator initially. This is also allowed, in which case numerator, that is b. We are basically factoring b. Okay, that is what we are doing. Can't we use the property 2 upon m? We did use the property 2 upon m. At the first stage itself we used 2 upon m. Here we calculated this using 2 upon m. In the last step, yeah, we can use that as well. Calculate it anyway, like, yeah, we can calculate it. So if we use 2 upon m, uh, 11 is, so it follows this. 11 is congruent to 3 mod 8. Therefore, it is minus 1. Yes, good observation. Yes. So we can use this as well. Multiple things, right? Either we can use the Legendre's symbol definition or we can use this. Okay, I'll quickly go through this definition, this thing once again. So 246 upon 257 we had. We factored b. This is of the form b upon m. So we factored this as 2 upon 257 into 123 upon 257. Now this is of the form 2 upon m. So m is congruent to, m is 257. So if you calculate mod 8, it is congruent to, because 256 is a power, so remainder is 1. So this is plus 1. It follows this. M is congruent to 1 mod 8. Therefore 2 upon 257 is 1. Then 123 upon 257 as it is. Then we want to calculate the reciprocal of 123 upon 257. This is calculated using minus 1 raised to m minus 1 into n minus 1 upon 4. Okay, so thus we get the sign of minus 1 as like, because this is an even number, minus 1 becomes plus 1. Then we calculate, now what we are using is we are factoring b upon m into b upon p1 into b upon p2 basically. So we tried this way, but there is an easier way in which basically there is another property which says that b upon m is congruent to b mod m upon m. So we just calculate 257 mod 123, which is 11. Okay, 11 upon 123 we got. Then we find the reciprocal, so minus 1 raised to m minus 1 into n minus 1. In this case it comes out as minus 1. And then we again use this property and we calculate 123 mod 123. We find that 123 is congruent to 2 mod 11, so it becomes minus 2 into 2 upon 11. And then we calculate 2 upon 11 by whichever way, either by using Legendre's symbol definition or by using 2 upon m rule, and we finally get the Legendre's symbol. Okay, so sorry, the Jacobi symbol for 247 246 upon 257. Okay, so what is the application of this? Now let's see an application of this. So this is called as, so this is clear. This was the calculation for any given pair of numbers for the Jacobi symbol. Now, if okay, if you want to find, so this is also called as Solovay-Strassens, Solovay-Strassens primality test. Excuse me for a minute. Excuse me. Okay, sorry for that. Okay, so Solovay-Strassens primality test. Yeah. So if I want to test the primality of some number n, so if n is an odd natural number, odd natural number, then n is prime if and only if the Jacobi symbol of a upon n is equal to a raised to n minus 1 upon 2 mod n holds holds for holds for all a holds for all a such that GCD of a and n is 1. Okay, so for any number n, you take the set of numbers which are relatively prime to n, and if you test this, a upon n is actually equal to a raised to n minus 1 upon 2 mod n. Now, how will you calculate a upon n? You will calculate using the different rules for the Jacobi symbol, and if it comes out as actually a raised to n minus 1 upon 2 mod n, then you can say that n is prime number. Okay, so we can check this for any prime number as such, but it's not required, like it's true. Okay, so this is called as the Solovay-Strassens primality test. What is a? A, so for example, if I'm considering 17, then I'll consider all possible, the like, or 16, any number you take, and a represents all set of all the relatively prime numbers to that particular number. Okay, but then again you will not straight away check all the numbers from 1 to n minus 1. Okay, again in that you will either go up to the square root of n, okay, or use some kind of an optimization, because otherwise it will become as good as the simple primality test, the brute force division test, trivial division that we had seen. Okay, and this is by no way the most the best test or anything like that. This is just one of the primality tests that is carried out using Jacobi symbol, and there are some more applications which are not there in the scope of your current syllabus and your current subject. But this is the Jacobi symbol, and if you want to explore it somewhere someday, you can explore it further. Similarly, in finding factors of large numbers, prime factors of large numbers, Jacobi symbol is useful. Okay. So, any more questions on this topic, or shall we move ahead? Okay, no questions. Okay, so I think the only topic left in, can you take one more example of? Jacobi symbol? Yeah, okay. Mm, okay, let's take a smaller example. 3 upon 35. You want to find 3 upon 35. How will you go about this? Okay, you calculate on your side. I'll give you 2 minutes, let's say. Think about it and let me know. Okay, so you will write this as 3 upon 5 into 3 upon 7. No, 3 upon 5, 3 upon 7. Like, yeah, there are only two answers if it is not. Okay, so how will you calculate 3 upon 5? 3 upon 5 is a legendary symbol. So you can directly do a raised to p minus 1 mod 5. Okay, or for 5 we had already done this. So 0 square, 1 square, 2 square, 3 square, 4 square. So it is this minus 1 in this case or what? This is by formula a raised to p minus 1 by 2 mod p and a raised to p minus 1 mod p for this one. So 9 mod 5 is 4. Okay, so in this case you'll just have to take care that you have to go either plus 1 or minus 1. Okay, so 4 is congruent to minus 1 and so this will become minus 1 and here 3 cube is 27. 27 mod 7 is 6. So 6 mod 7 is congruent to minus 1 again. So therefore it is plus 1. Okay, very simple example. Any question on this quickly or did you get this, every one of you? Yeah, reciprocity gives you 2 upon 3 in both cases, right? That is also possible. This is also okay. Use any law. Okay, so plus 1. Everyone agrees with this? Okay. So the next, the last topic in this first module is the birthday paradox, which will uh, which will require us to revise some concepts of probability again. So Okay, so what the birthday paradox says that there are 23 people in a room. I think I had mentioned this even in the digital forensics first lecture. Okay, so birthday paradox. What it says that if there are 23 people in a room, okay, then there is a 50% chance of at least two people. Okay, there is a 50% chance or 0.5 probability that at least two people have the same birthday. Okay, and further extending this, if there are 75 people, if there are 75 people in a room, there is actually a 99.99% chance in terms of probability. If you say it is 0.9999 or 0.999, that this is the probability that at least two people, same thing, have the same birthday. Okay, so why this is a paradox? Now this is completely true. Mathematically this is completely true, but it is a paradox because as a human we cannot handle the fact that there are 365 days in any year. Even if you exclude 29 February, there are 365 days, and among so many days, what is the coincidence that two people have the same birthday in a room of just uh, 23 people or 75 people as such? So now there are many other examples that we can have. Uh, okay, so let's directly get to the probability calculation. So what is the chance of getting one or more heads in 23 coin flips? Okay, if there are 23 coin tosses, what is the probability of at least one? That is, what is the probability of at least one head? One or more. So at least one head. So how do we solve this? We solve it by finding the probability of the complement of this event. So what is the probability that there is, what is the probability that there is no head? There are all tails. Yeah, 1 minus 0.5 raised to 23. So I'll quickly, okay, so 0.5 on every toss is the probability of getting a head or a tail, fair coin. So probability of getting a tail on every toss is 0.5 raised to 23, and the complement of that is 1 minus 0.5 raised to 23. So if you actually calculate this, you can say that there is 99.999 something chance of having at least one head. Okay, so in the same way, in case of this birthday problem, what is the chance that everyone has a different birthday? Then we take the opposite of that probability and we get the chance of at least one match. Okay, so in case of this 23 people, we have okay 23. So how many pairs do we have to check? So 23 n into n minus 1 upon. Okay, now this is again I'm back to the birthday problem. Back to the birthday problem. So 23 upon 20, 23 into 22 upon 2. That is 253 pairs we have. Okay, this is one thing. And the chance of any two people that you pick to have different birthdays is what? You ask one person. Let's say today is 16th June. So what is the probability? What is the chance of two people having different birthdays? So the chance of both of them having the same birthday is 1 upon 365, or no, uh, this is not the logic. We want to find the probability of both have different birthday. Yeah, 364 upon 365 is the correct answer. Yeah, 1 minus 1 upon 365. Okay. Okay. So simply if I say in 364, so there is only one favorable scenario or one favorable day uh, out of all 365 in which they may match. So the complement of that is there are 364 out of the 365 days, 364 out of 365 days that they won't match. Okay, so using these facts, so this is like we have 253 tosses, and this is the probability of uh, what you can say, probability of all tails. Let's say so. This is 364 upon 365 divided by raised to the power 253. Okay, now can you calculate this? Actually, the value is 0.4995. The value for this is 0.4995. It's there. Okay, it's just there. And if you do 1 minus this, that is 1 minus the probability that both will have a different birthday. then it is actually 0.5005. Okay, so in general, if we want to find the probability for any n, that is if there are 10 people in a room or if there are 50 people in a room, so Pn is 1 minus 364 upon 365 raised to n into n minus 1 by 2. This is the number of possible pairs. This is the possibility of having a different birthday for each of them and the complement of the entire thing. This is the probability. Now, okay, so any questions up to this point? Any doubts? N is the number of people in the room. Yes.
Sir, in the previous Jacobi example, in the second example
Of?
of Jacobi,
Okay.
yeah. So we got four, na, like 9 mod 5, we got 4, and
Yeah,
4 is a
yeah.
perfect square.
Yes, you can go, see, you can directly use the Legendre symbol itself has two definitions. Either you
Okay.
can go by the perfect square mod p, or you can use a raised to p minus 1 by 2 mod p, or you can, if it is 2 or minus 1 or anything like that, but 2 upon m format, you can use that. So in this case, yes. What was the question then?
So, sir, if we would have taken the perfect square one, so we would have got plus 1 there, right? Because 4 is a perfect square, so it would have been plus
No,
1.
4 is a perfect, no. Okay, we can apply it here. So a is a perfect square mod 5 or not. You don't
Acha.
apply it here. Okay, now here we have started using a raised to p minus 1 by 2 mod p. Then we don't apply perfect square. Okay, either go perfect square way or this way.
Okay.
Okay,
Okay.
so with this we come to an end of the first module of our syllabus. And what is the application of this birthday paradox is, it helps us to find the probability of uh, a birthday attack, that is a collision. Okay, so there is something called as birthday attack in cryptography, and to calculate that probability we can make use of this particular format, the birthday paradox. It is called as birthday attack. Okay, so we can calculate the probability of birthday attack. Calculate the probability of birthday attack, cryptography. Okay, so that's it. Okay, then if there are no questions, I'll end the lecture here. Any questions? Okay, I'll. Thank you.